Hello and welcome to the 39th episode of the podcast. Today I'm going to expand the scope of my ecological examination, going from behavioral ecology, which I talked about in the last episode, and expanding to population ecology. Where behavioral ecology examines the actions, patterns, and responses of an individual organism, population ecology examines the actions and responses of whole groups of organisms. These groups are called populations, and they're composed of a number of individuals of the same species, all living and eating and migrating together in the same physical habitat, in the same general area. Just like an individual organism has patterns in its behavior, so too do populations. If the actions of an individual causes an effect, then a group of individuals all making the same actions will cause a meta-effect. Some examples off the top of my head, swarms of locusts or herds of wild horses, or some kind of like a wild grazing species. They'll occasionally move through an area and they'll eat so much of the local foliage that they'll destabilize or outright destroy native habitats, native ecosystems. Another example is that predator and prey population sizes have a cyclical relationship based on the carrying capacity of their food. I'll go into all of this and more in greater detail today. So if you were to try and understand a population, how would you start? What would you look at? What would be the first perspective you would take in examining the population as a living thing, as a group or a causer of meta-effects? A basic place to start is the range of the population, or the geographic regions where the organisms are naturally found. Some animals have very large ranges, like brown bears and black bears, which live in Alaska, Canada, and down into the central United States near the Rocky Mountains. And they also exist in most of Asia. Monarch butterflies are another species that has a really huge range. They migrate between the southern parts of North America, near Mexico and Mesoamerica, and in the summertime in the northern hemisphere, they all migrate back north across the United States, Canada, even reaching as far up as Alaska. So their range is basically the entire North American continent. There's also various kinds of migratory birds who fly between habitats separated by thousands and thousands of miles. All organisms have a range that extends out to some fuzzy border, because there isn't a single organism naturally adapted to every type of climate and biome. Consider us humans. With our technology, like mobile shelters and climate-appropriate clothing like snow pants and boots and jackets and sealed food and stuff like that, we can live in almost any habitat. But when you strip from a human their technology and you put them naked into a wild environment to fend for themselves, using just their body as was created by natural selection and evolution, we would find our range drastically reduced. No humans would be able to survive a snowy and icy winter, so no humans would be able to live in much of North America, Europe, and Asia. A naked human living in the wild, basically like our ancestors did more than 50,000 years ago, would only be able to survive the dry, warm climates of the African savanna, of the warmer parts of the Mediterranean, or India, Southeast Asia, or Australia, where it's annually really warm and with a steady climate. Outside of these areas, though, the climate is unforgiving to the human body. The temperature and the seasonal changes are too brutal for humans to withstand without our clothing and our shelter. All of these are factors of the abiotic aspects of the world, and they influence the range of the species. Just like the cold of winter limits the natural range of humans, the heat of deserts and the tropics repels those species more acclimated to polar regions, like polar bears or the seals that they feed on. Polar bears have a range that's limited by more than just temperature and climate, though. The polar bears use ice sheets and floating chunks of ice, almost like a fishing platform, and they float a little bit out into the Arctic Ocean, where seals are, and they catch seals and eat them for their fatty tissue. Without access to their primary natural food source, which is these seals, a polar bear can't live for very long, and so the range of viable habitat for the polar bear is tightly correlated with the ringed and bearded seals. The seals swim in the Arctic Ocean, coming up to breathe or sometimes to wash up on the ice and take a break from swimming. On land, or I suppose on ice, The seals are much less agile, and a quick polar bear can catch and kill one. The fact that the polar bear's range is limited by the availability of these seals is an example of a biotic factor instead of an abiotic factor. Both abiotic and biotic factors influence the range of all populations, from animals to plants to fungus. Reptiles need the heat of the sun or of the tropics. Amphibians need the humidity of the jungle or a swamp. And polar bears need their Arctic ice. All of these are abiotic factors caused by the geography and climate of their habitat. Biotic factors, on the other hand, are living things or the products or effects of living things that influence or limit the range of other organisms. In this case, the seals are a biotic factor for polar bears, but this kind of food dependence goes way beyond the Arctic. Various populations of bees are dependent on the flowers that they feed from, as are moose by the willows they eat, and predators like wolves from the prey species that they eat. Disease is another factor that influences range, like the avian flu and Hawaiian mosquitoes, which drive much of the native birds up into higher elevations in the mountains. Within their range, a species is not typically distributed equally across geographic space. They might be randomly distributed across the land. This means that the position of one individual doesn't really affect the position of another individual. If you imagine a shrub-like plant, it would release spores or seeds or something, and these could catch the wind or cling on to an animal's fur and be taken 10 inches or 10 miles away from the parent plant. It's a pretty random distribution. Sometimes the distribution of organisms is influenced by the geography or by the animal's social behavior. If you're an animal in the desert, chances are you and your population are going to dwell around a watering hole or an oasis or something similar. In other cases, the animals exist in groups or clumps, like a herd of grazing cattle or a herd of caribou, a school of fish, or a family of prairie dogs. If an organism is competitive or aggressive towards members of its own species, then the population won't really be naturally distributed in social groups and clumps like that. In solitary species, the distribution of individuals across the landscape is actually more or less uniform. Now, when I say the distribution is uniform, I mean that there's roughly the same density of individuals across geographic space. This is because the individuals compete for food or water or territory or some kind of limiting resource. Instead of cooperating and living in clumps like a social species, the populations of more solitary organisms are uniformly spread out across a mosaic of hunting and mating territories, each one belonging to one individual, and perhaps their not yet matured offspring. The borders of these mosaic territories are defended either really aggressively or, they're barely even recognized at all by the species in question. It just has to do with the species you're talking about. Okay, so now we've started with the population's range, with the extent and the patterns of their geographic distribution. Let's zoom in a little bit and look at the population itself, at the number of individuals in the population and how fast they die, how often they leave or join a group, and how fast they reproduce. These factors are called the population's demography. The size of a population can grow when individuals immigrate into it or when there's a new birth. And in just the opposite way, the population can shrink if individuals start emigrating away or if they die. To study these kinds of things in various organisms, biologists use a probability summary called a life table and an analytical tool called a life history. The life table looks at an organism's actions over its lifespan. How old does it get before it dies of old age? What's the probability that the organism will survive and or reproduce in a given year of its life? The life table breaks down this data into a series of columns based on age, number of survivors, and their proportion, their rate of reproduction depending on their age, and the average birth rate over time. That was kind of a lot, so let me break this down so it's a lot nicer and simpler. In the first column of a life table, generally on the left if you're seeing it as a written diagram, we have a list of the typical lifespan in numbers of years. So for example, if an organism has a maximum age of 10 years, this column will simply be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The next column lists the number of survivors. I'm trying to keep this simple, so let's say that we're just looking at a population of frogs. If a population of frogs has 1,000 offspring in a breeding season, then the number of survivors at year 0, at the very beginning, is 1,000. But life is tough for these little frogs, and whether it be through disease, predation, or accident, or any number of things really, only 500 make it to their first birthday. At year 1, the number of survivors is 500. These survivors are a little hardier, a little more experienced, and so 300 of them are able to survive to year 2. 250 frogs survive to year 3, and 200 survive to year 4. If we go down the years, we might see that only 10 frogs out of the original 1,000 survived to their 10th birthday. You might have noticed that this is a rate of survivorship, which is the third column in the life table. In year 0, we had 1,000 newborn frogs with no deaths. Survivorship for year 0 is 100%, or a ratio of 1.00, or 1. But by year 1, half of the frogs had died. This means that year 1 has a survivorship of 0.5, or 50%. By year 2, only 300 frogs were still alive, representing a survivorship ratio of 0.3, or 30%, 300 out of 1,000. This goes on until year 10, where we have just 10 survivors, representing just 1%, or a ratio of 0.01 to the original population. The next column is the rate of reproduction based on age, or more technically, the age-specific fecundity. Let's say that frogs are too immature to have offspring in year 0 and year 1. By year 2, some of the frogs are mature enough to have offspring, but some aren't. But by year 3, all of the frogs are mature enough to reproduce. The age-specific fecundity column tracks the average number of female offspring had by an individual female frog in each year of her life. If you multiply the survivorship rate by the age-specific fecundity, you derive the 5th column of the table. Now if you multiply the survivorship rate by the age-specific fecundity, you derive the 5th column of the life table, which is the average birth rate per year per breeding female. Or more simply, you get the reproductive rate. In my example, we have a population of frogs that die off pretty quickly in their young age, but reproduce more often in their old age. What the life table would show us is that most frogs are being born to frog mothers of intermediate age, around 3 or 4 years old. When you multiply the survivorship rate with the age-specific fecundity of that year, you get that year's reproductive rate. And if you add together all of the reproductive rates for each year of life, because remember, reproductive rates aren't constant through life. You reproduce more often in middle age than you do as an adolescent. So if you add all of these rates together from all of the years of life, you'll get a number called a net reproductive rate. If the net reproductive rate, if the number for that is 1.00 on the dot, the population is stable. It isn't growing, but it isn't shrinking. It's staying the same. The rate of births is keeping up with the rate of deaths, and the population is stable. But if the sum is less than 1, this means the population is shrinking. The rate of births can't keep up with the rate of death. If the sum is more than 1, it means the opposite, that the population is growing. The birth rate is exceeding the death rate. By using life tables, biologists can keep an eye on the fluctuations and moment-to-moment glimpses of the growth and death of various populations. This kind of data can also be used to derive survivorship curves. These survivorship curves are lines on a graph that show how age is distributed in a population, where the age of the organisms is on the x-axis, and the number of surviving individuals is on the y-axis. All survivorship curves start at the top left corner, where the number of survivors at age 0 is 100%. This is like my frog example where they had 1,000 frogs at year 0, 1,000 newborn little frogs. All of them are surviving, none of them have died yet, we got a full 1,000. That's where the survivorship curve starts, at age 0 with 100% survivors. But they all end at the bottom right of the graph, where the number of survivors at the maximum age is 0. The interesting part about these curves is how they're shaped in between those 2 points. A type 2 curve is the simplest curve. It's more or less a straight line or close enough between the top left and bottom right corners of the graph, representing a species that faces roughly the same rate of death in every year of life. All of the textbooks that I have on hand, they repeatedly cite songbirds and various other species of birds as that with a type 2 survivorship curve. Songbirds are just as likely to die at age 1 as they are to die at age 5 or age 10 or however long they typically live. But other species have a type 1 or a type 3 curve, and these are a little more interesting. The type 1 curve shows a high rate of survivorship in early life, representing a majority of individuals surviving through infancy and childhood into adulthood, with survivorship eventually but suddenly dropping off as the individual reaches the end of its lifespan. A type 3 curve is the exact opposite. The survivorship of the young is really low, so the curve drops down really fast. By year 1, you have 20% survivors. By year 2, you've got 8% survivors, or something like that. That's a type 3 curve. But after the type 3 curve drops down really fast, it suddenly levels out asymptotically near the bottom. And this represents the fact that mature individuals, or those few who do make it to maturity, have relatively long lives. To put both the type 1 and type 3 curves in context, consider humans and trees. Humans are a species with a type 1 curve. We put a great deal of care into our offspring, and we try to maximize the survival of our children into their adulthood. We have a high survivorship in childhood, and in most of adulthood, but past a certain age, like 65 or 70 or 80, depending on the individual's physical health, the rate of human survivorship begins to rapidly drop off. Of course, there are some exceptions where people live to be 90 or 100 or, in extremely rare cases, 120, but we're talking about general trends here, not the extremely rare cases. The human type 1 survivorship curve shows high survivorship in youth, but low survivorship at the extreme end of the age range. Many trees, on the other hand, have a type 3 survivorship curve. This means that many trees die young. Most trees, actually. But those that survive past childhood and mature are likely to have a long, full life. Consider a tree that reproduces with seeds. The seeds have a huge death rate. They get crushed underfoot, or eaten, or they rot, or they just land on rocks, or they just fail to germinate, or any of 1,000 things. But of this tiny fraction of surviving seedlings, a huge portion are then killed by herbivores, or harsh weather, or by mechanical damage from some trampling animal, or a geological event like a landslide or a flood. It's only a very, very small sliver of the original seed population that grows into another mature adult tree. But trees are strong and sturdy, long-lived, and difficult for nature to kill. Once the tree has established itself and developed a thick trunk of hard woody tissue and a penetrative root layer that reaches deep into or across the soil, it can survive for hundreds and hundreds of years. This is a great example of a type 3 survivorship curve, where the young organisms have an exceedingly high death rate, but the mature organisms are much sturdier and less likely to die in any given year. Alright, so I mentioned life tables, which I just went over, but I also mentioned something called a life history. The life history is a reflection of the life table, but it takes into account a few more variables, like differences between populations in different regions, like faster or slower birth rates, or a greater or lower fecundity, or a difference in the rate of deaths in certain years. It shows kind of an evolutionary context, like a more long-term evolutionary context, where the life table is more like a snapshot in time. All of these rates are influenced by things like the local climate of the habitat, the available nutrients and food sources, and the kinds of predators and assorted threats that the population would be exposed to. All of these things are context sensitive to specific populations at their specific locations. In my hypothetical frog population, no frogs reproduced at age 1, but it's quite possible that some populations of frogs somewhere else, of a similar or closely related species, might exclusively reproduce at age 1 in response to a shorter lifespan caused by heavy predation or disease. In a region with low predation and abundant food, the situation might be reversed, and the frogs may be long-lived, with a low fecundity, only beginning to reproduce at age 4 or 5. So why do the life tables vary between populations? You'll notice that each of these hypothetical populations is exposed to different variables, different amounts of available food or predators. Individuals in certain habitats need to find some way to balance their resource use to keep themselves alive while also creating healthy offspring. In order to balance their resource use, the organisms need to engage in fitness trade-offs, which is a defining aspect of their life history. The life history is, most fundamentally, how an organism prioritizes its resource use. Does it invest a lot in developing a strong immune system? In tropics where diseases are prevalent, this probably wouldn't be a bad idea. But in the polar regions where there's little to no native diseases, it would probably be a waste of resources. Does the organism invest a lot of time and energy into their offspring? Well, that depends on the mating strategy. Species like elephants and gorillas don't reproduce that often, so they have the capacity to invest a lot of time and energy into protecting and feeding their offspring. They care for the offspring for a long time after birth, and they raise it to maturity before it wanders off to live on its own. But species of insects and fish will usually have dozens, if not hundreds, of offspring. They just lay a ton of eggs, in the best hope that some of them will survive to adulthood. And so they can't possibly invest time and energy into each one, there's too many. So instead, they just focus on sheer quantity over quality. They embrace that aspect and just try and pop out as many offspring as possible in the chances they're just rolling the evolutionary dice in the chance that one of these many hundreds of eggs will make it to maturity and reproduce again and perpetuate the genes through time. If an organism lives in an area with a large number of threats, where mortality is high, the organism would be encouraged to reproduce sooner and more frequently to ensure it can pass on its genes before it too dies of predation or disease or whatever it is that plagues them. In the opposite sense, an organism in a safe environment with plenty of resources and no predators can choose to take their time, reproducing later in life and only producing a few offspring that get a lot of love and attention. These are all fitness trade-offs, and they define the life history of not just a particular species, but of specific populations within that species. Life history, or life strategy, is all about maximizing fitness in the particular environment the organism finds itself in. But keep in mind that developing these adaptations and maximizing the species' fitness doesn't take place on an individual level. It takes place on a population level, over many, many, many lifetimes. The life history patterns of the individual are mirrored in the entire population, which naturally shares the same habitat and the same exposure to food and to parasites and disease. When you look at life histories across species, you start to see a kind of spectrum, with high fecundity or a high reproductive rate, but low survivorship on one end of the spectrum. This is like insects and fish. And on the other end of the spectrum, you see a low fecundity, but a high survivorship, like elephants or humans. Those organisms with high reproductive rates and low survivorship tend to have shorter lives, characterized by faster growth and maturation, earlier reproduction, and larger numbers of offspring per clutch or birthing event. In contrast, species with low reproductive rates and high survivorship are generally longer lived, with a slower rate of maturation, who reproduce later in life, and who produce a smaller number of offspring. These strategies all contribute to the population's growth rate. Recall the variables I mentioned earlier that influence growth rate. Births and deaths, obviously, but also immigration and emigration, as individuals move into a new population or leave an original population to join another. This is often called gene flow. I talked about gene flow in greater detail in my episodes on evolution, which you can check out in another playlist. Growth rate is a pretty technical aspect of population ecology, involving a sizable amount of math and various equations. I considered getting into the technicalities and the mathematical weeds of population growth, but ultimately, I realized it wouldn't be a very exciting thing to listen to. So with that said, I'll try and explain growth rates without really diving into the math and technical theorems behind it. Just know that this aspect of studying biology is pretty heavily dependent on mathematical models and calculations that identify and track and predict patterns. Alright, so every population has a death rate and a birth rate, and the ratio between those two rates is called R. If the birth rate exceeds the death rate, then the population is growing, and R is a positive number. On the other hand, if the death rate exceeds the birth rate, then R is a negative number, and the population is shrinking. In some cases, a population may experience the highest possible birth rate and the lowest possible death rate, which implies they found a more or less optimal living situation. In this case, the R value is called R sub max, or just R max, which means that the population is enjoying a maximal growth rate. If a population is growing, and its R value is positive, it can be undergoing either exponential or logistic growth. If the R value stays the same, that is to say, if the ratio between the death rate and the birth rate stays the same through time, then the population is experiencing exponential growth. To illustrate this, just imagine a population of 100 individuals with an R value of 0.05 per year. In 1 year, the population will grow from 100 to 105, and the next year it'll grow to 110, then 116 the year after that, then 122 after that, and so on, increasing by 5% of the previous year's number, of the previous year's population, and this will happen every year. So if you have a starting population of 1 million with the same R value, then in 1 year the population will grow from 1 million to 1,050,000. The year after that, it'll be 1,102,500. Then the year after that, it'll be 1,157,625. And on and on. Now imagine if you have a population like 7 billion, which the human species has today. How fast do you think the population will grow in the next 10 years, or 50 years, 100 years? Do you think we'll reach an upper asymptote where the population growth will level off and maybe even suddenly drop from some variable like a disease or a plague or a war? Anyways, the thing to ultimately take away from this is that the growth rate doesn't change from year to year. The R value for these hypothetical populations, both the small 100-person one and the million-person one, it's the same growth rate. It's 0.05. And this doesn't change, even though the population is getting exponentially larger. The growth rate remains the same. That's exponential growth. It's really important to understand, however, that exponential growth is seen really only in populations that are small or new to a certain habitat, because exponential growth cannot go on forever. You cannot have a population that just grows and grows exponentially forever, because there will come a point where the number of individuals exceeds what the habitat can support. There's simply not enough nutrients or whatever other vital resources necessary to support a population any larger than the one that exists now, at the maximum size. This upper limit is called the carrying capacity of the habitat. When you look at human population sizes, you'll often hear people talk about the carrying capacity of the planet. When a population size reaches carrying capacity, the death rate will increase and surpass the birth rate. The R value will lower and eventually become negative, and the population will begin to shrink. In this way, logistic growth is different from exponential growth because it does depend on the number of individuals present in the population. If there's a small number of individuals, the population is nowhere near carrying capacity, and the growth rate is probably pretty high. But as the population grows, the resources in the habitat start getting used up faster. There's more competition for food, more competition for shelter, more competition for mates. The larger population can support a larger predator population, and predation becomes more and more common. When food is gone, starvation becomes more and more common. All of these factors cause the growth rate to slow until it ultimately falls to zero when the population reaches carrying capacity. If you were to graph this population growth with time on the x-axis and population size on the y-axis, the curve would look like a stretched out S, with its upper and lower slopes running along horizontal asymptotes. At the low end of the y-axis, population growth is slow because the population is small, but it increases rapidly over time as the individuals spread out to fill a habitat and exploit its resources. For this brief, temporary window of time, the species is exhibiting exponential growth. But at about the midpoint up the y-axis, the population size has increased such that there's now noticeable competition between individuals. It's clear to everyone in the population that resources are becoming a little more difficult to come by. It isn't as easy to feed yourself as it once was, because there's more and more competition. The growth rate starts to slow, and the growth curve flips. Instead of continually increasing at a faster and faster rate, the rate of increase begins to slow down. When the population size reaches carrying capacity, or the upper horizontal asymptote on the graph, the growth rate levels out again by nearing zero. The population will fluctuate up here, unless some massive death event like a disease, or a volcano eruption, or an asteroid strike, or a swollen predator population comes in and cleans house, and more or less resets the population back to a much smaller size. The growth rate of a population is tightly limited by these density-dependent and density-independent factors. You can think of density-dependent factors as things that would limit population growth when there's a lot of individuals crowded together in an area that's too small for them all. Consider trees in a forest. If there are too many trees, they start to crowd each other out. The canopy might block out sunlight and kill younger, smaller trees. Or they might struggle to get enough water, what with all the other trees nearby soaking up as much water as they can. When rats live in a high-density population, they begin to experience something called a behavioral sink, where normal rat social behavior breaks down. Social cohesion breaks down. There was a really fascinating experiment conducted by a scientist named John B. Calhoun, who created what he called a rat utopia. It had abundant space, ample food, and no predators. The mice who first inhabited the utopia were quite happy, as they could live leisurely lives of eating and mating all day without fear of getting eaten. Naturally, with no brakes on their population growth, the number of rats rapidly exploded, and they soon filled out their utopia. What happened next was both endlessly fascinating and endlessly horrific. The rat population experiences a host of serious problems that basically destroyed their little rat society. With too many individuals crowding the available space, the rats were unable to find privacy, and they were thus unable to form strong social bonds. They couldn't form long-term or serious relationships because they could never achieve the social space or the environment to develop those bonds. It was just too crowded. It's like trying to really get to know somebody in the middle of a nightclub at 2 a.m. After this, birth rates plummeted, and of those female rats who did give birth, the majority were terrible mothers who neglected or killed their offspring, or they killed the offspring of other mothers. Infant mortality reached as high as 96%. Some males engaged in rape, in cannibalism, and in excessive conflict, while other males totally shut down and hid themselves away, only coming out to eat and move around when others were asleep. Malnutrition, starvation, and violence became endemic in this rat society. Such is the harsh reality of nature when a habitat, even a so-called utopia, exceeds its carrying capacity. Other density-dependent factors include diseases, which spread faster in denser populations, as well as predators, parasites, interspecies competition, and other biotic stuff like that. Density-independent factors tend to be abiotic, and they have the same effect on a population no matter what the population size is, no matter how many individuals there are. These include things, natural events like an earthquake, or a flood, or a volcano, or an asteroid strike, or a harsh winter, or the pH of the ocean water, or anything like that. In this way, density-independent factors can affect large and small populations, dense and spread out populations, and it can have any kind of effect on them. A harsh winter might kill a few voles in one population, but that same winter might totally wipe out another population of voles. It really depends on a hugely complex confluence of variables. The last thing I want to cover today is population cycling, or more specifically, the cyclical nature of population sizes that exists between prey and predator, or of host and parasite, and in a way, between two species competing for the same food source. In all of these cases, the populations experience cycles. Consider the predator-prey relationship between a small herbivore like a rabbit and the predators that feed on them, like a fox. The rabbits eat shrubs and grasses, and as they do so, their population grows. The rabbit population will grow until they start to run out of food, until there's so many rabbits eating so much grass and shrubs that all of a sudden there's none left for anybody. At this point, the rabbit population crashes as it experiences widespread starvation. After the crash, the rabbit population is small. There's only a few survivors who manage to eke out an existence. But this small population needs less grass to sustain itself. And that's good because there's less grass around because they ate all of it. But this lull in plant-eating activity by the rabbits allows those grasses and shrubs to grow back. And in time, the population of rabbits will grow once more to feed on all the new grasses and shrubs. In this way, the rabbit population cycles between large and small, just like the population of shrubs and grasses in that rabbit's habitat also kind of cycles along with the pattern of the rabbit's eating behavior. So where are the foxes in all of this? Well, the foxes feed off of the rabbits. And so when the rabbit population grows, the foxes suddenly find that they have a lot more food available to them. They can eat more, they can catch things easier without spending as much energy. They can sustain more offspring. And in time, the fox population will grow larger too. But remember that the rabbit population crashes. And so for a time, this swollen fox population will struggle to find any rabbits to eat. All of a sudden, that ample rabbit food that they were experiencing before, it all went away as the rabbits ate up their food and died off. Well, now the foxes are starving and they're dying off. And the fox population experiences its own crash. Now that there's fewer predators harassing the tiny rabbit population, those rabbits can more easily spread back out and rebuild their numbers. When the rabbit population grows again, the fox population can grow back as well. In this way, the population of predator and prey cycles up and down, with the predator cycle on a slight delay behind the prey cycle, which makes sense as the foxes have to actually notice the lack of rabbits and start starving before they die. They don't just immediately starve the moment the rabbits do. This cyclical trend also holds true for parasites and their hosts. In large populations, the parasite can spread to a huge number of individual hosts, and their population will explode. But if the parasite decreases the host's fitness, or if it outright kills the host, then in time the host population will shrink, because they've all been infected by these parasites, or the parasites have just had a really serious penetration rate into the population, and so there's huge infection rates, and thus huge death rates. When the host population shrinks, the parasites find themselves without a home, without shelter and food, and they too will experience a shrinking population. Well, that about does it for this episode on population ecology. I hope you found it as interesting and as exciting as I do, and I hope you were able to learn something that you think is pretty cool. I think population ecology is so fascinating because it's the study of life as it spreads out across the landscape, as its population sizes swell and shrink, and as it responds to the abiotic and biotic factors in its environment. Stay tuned next week for my episode on community ecology, where I talk about the interactions between multiple species all existing in a habitat. And as always, thanks for listening.
Would you like to support the BioLogic podcast? It's super easy. When you open a new episode, press the like button or share it with your friends. If you aren't subscribed, you should hit the subscribe button so you can enjoy a new episode every week. You can also peruse our official store, which has a ton of cool stuff like hand-designed t-shirts, hoodies, and stickers. All the links you need are in the description section below.